Assalamu alaikum, hi everyone. Welcome to our webinar, Reservoir Modeling Workflow. I am Abdullah, a business developer into Reservoir Solutions company. First of all, we will start with 5 minutes presentation about Reservoir Solutions, and then Mr. Muhammad will start our webinar for today. So for Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researchers like PhD and master degrees. Also, we are assisting in writing technical papers and publishing. Also, we are providing technical petroleum courses by industry experts, and we also provide mentorship programs. Just we wanted to announce our next course, which is static and dynamic reservoir modeling, which will start on 25 on July. That will last for 2 weeks, and it will be a practical course. For the course content, the course will be 2 weeks, and by attending this course, you will enjoy lifetime access to the recorded sessions, so you won't worry about the timing of the sessions. Even after the course, you can have access to the recorded sessions. Also, you will enjoy application datasets, application-based workshop. The course material will be provided. We will have 2 days project at the end of the course to confirm full understanding. You will have open discussion with instructor during and also after the course. Also, at the end of the course, you will have a certificate with online identification ID on our website. By the end of the course, you will be able to do well correlation, upscale well logs, visualize seismic outputs, do structure modeling, faults and surfaces, do facial modeling and distribute petrophysical properties, calculate volumetric oil in place, static geologic modeling QC, upscale fine grids to simulation coarse grid, incorporate PBT and scale data in simulation model, learn well placement and design techniques, learn history matching principles, do well optimization, and do field development planning. And at the end, you will also be able to do uncertainty and sensitivity studies for volumetric and simulation studies. For the course content, I will provide a link to view the details of the course content. For our webinar today, Reservoir Modeling Workflow, the instructor is Engineer Muhammad Amin. Engineer Muhammad Amin is a senior reservoir engineer at Mineral Petroleum Company in Egypt. He has more than 9 years of experience into asset evaluation, reservoir characterization, and simulation. He participated in and recently managed many successful field development plans in green and brown fields within offshore Gulf of Suez area. Muhammad has a correlation that follows his name in field of reservoir fluid flow modeling. He holds a bachelor and master degrees in petroleum engineering from Suez University in Egypt. He has many publications into several journals and conferences like MBM, IGRTE, and B&C. For the webinar rules, kindly, if you have any questions, you can ask them into the Zoom chat. Also, mute your microphone and camera. In case that you want to have a certificate for attendance for this webinar, you should fill into the form that will be sent at the end of the webinar into the Zoom chat. For upcoming webinars and courses, you can join our Telegram channel and follow our LinkedIn profile. Also, you can contact us via mail and mobile or WhatsApp. Also, I want to remind you that if you want to enroll into the upcoming course, Actually, we have 3 seats now. So if you want to catch one of that 3 seats, you can enroll into the course through the link that will be sent into the Zoom chat. Thank you all, and Engineer Mohammed, you can start.
Thank you, Engineer Abdullah. Sorry for the delay. Just I was adapting my PC. So, Assalamu alaikum. Welcome everyone to our webinar Reservoir Modeling workflow. Our agenda for today, we will talk about the exploration and the production upstream life cycle. Also, we will talk about the reservoir modeling importance and the cases at which we should use reservoir modeling. Then we will speak about, or we will talk about the main topic of our webinar, which is the reservoir modeling workflow for static and also dynamic models. First of all, just to know that is the cycle for the production. The cycle for production for any field, we start by the exploration. First of all, we should evaluate our field or our reservoir by drilling. And also we have initial seismic data. Depending on that seismic data, we will decide to have exploration well. Okay. Then we will have other wells to delineate and further explorate our field. Then we install the production facility, then start the production. Then at the end or at decline of the production, and before the decline of the production, we have some plateau at which we conserve our production at certain limit. Then when the decline occurs, so we will start to have secondary recovery application like water injection or gas injection. Then at the end we will have EUR stage. Then we will abandon our field. Okay, so through the cycle of exploration and production, we acquire some data. So initially we have seismic data, and also from the exploration drilling, we will have further data about our reservoir. Okay, then appraisal drilling also, we will have we will gain also some additional information about reservoir, and that will help us into the development studies and optimization of the development for our reservoir. Okay, just I want you to know that during the cycle of that production, we acquire some data depending on the knowledge of depending on our knowledge about our reservoir. We can go for reservoir modeling, and also the accuracy for reservoir modeling will be higher and higher during or with the further development activities into the reservoir. Okay, so when we should use reservoir modeling, you should know that reservoir modeling is a general term. Okay, usually we are calling reservoir modeling when we go to using some softwares like Eclipse and Petrel. Okay, but the reservoir modeling or the modeling in general, just to have a mathematical model, and this mathematical model should represent a natural phenomenon. For our example, for our case into the oil and gas industry, we have mathematical models like what? Like the decline curve analysis, like the material balance, like the reservoir simulation, the numerical reservoir simulation done by Petrel and Eclipse, uh, like the well test. All of that are mathematical equations. Okay. So modeling is just to have a mathematical representation by a certain phenomenon. That is the modeling. Okay. So we have a general rule into our industry. When you go to directly to reservoir simulation, you should know that you will have additional cost to your project, and we should decrease the cost of production and exploration into your reservoir. Okay, so we shouldn't go directly to reservoir simulation or the numerical reservoir simulation. Okay, you can use some traditional methods for reservoir simulation or reservoir modeling, okay, like the decline curve analysis and the material balance and so on. Okay, so in case that methods are not sufficient or are not providing some data that you need to further develop your reservoir, so in that case you should go to reservoir simulation. Okay, like what? Like in case that you want to compare between the flank water flooding to better water flooding. Okay. In some cases, we want to know the best locations for the water injection or the gas injection wells. Okay. So in that case, the material balance and the decline curve analysis want to provide you by this piece of information, the location to drill the next wells. Also, in case that you have a breakthrough for the water and you wanted to know the location for the unswept oil, also the material balance and also the well test or the decline curve analysis or any of the methods of the traditional reservoir modeling won't provide you by this piece of information. Okay, in general, in case that you have high effect of capillary forces, that in case that you have tight reservoirs or low permeability reservoirs or having high viscosity fluid, like you have low EBI oil, or in case that you wanted to ask a question or to have a certain piece of information about the location for wells, the locations to drill horizontal wells and so on. So in that case, you can go to reservoir modeling. For the workflow, you should know that the reservoir modeling process is an integrated process. Okay, so all the disciplines will be integrated into that process. Initiating from or starting from the geophysics. The geophysics will tell us about the surfaces for the reservoir, will tell us about the locations for the faults. Okay, will tell us about will tell us about the boundary for the field and so on. The geologist will do or will do prediction for the fishes. What is the depositional model for our reservoir? Is it a meandering channel? Is it a delta fan? Or it's a carbonate? So we have different depositional models for carbonate and so on. For the petrophysicist, first of all, you should have the well logs interpretation. Okay, then the petrophysicist will integrate the well logs interpretation with the core data to have property modeling, like construct a relation between the porosity and the permeability, or also doing the rock typing task. The rock typing task usually is done by petrophysicist or the reservoir reservoir engineering. Then at the last, after doing all the tasks by the G&G team, so the result of that work will be the static model, Then this static model will be handled to the engineering or the simulation engineer. So the simulation engineer will input some data like the PVT data and the scale data, the production, and the proposed wells. Okay. Then first task of reservoir engineer or the simulation engineer to QC the static model, Then after QCing the static model, he will input the dynamic data like PVT scale and start doing the history matching and the prediction. Okay, let's go into details for the static model and also the dynamic model. Okay, so first of all, we will talk about the static modeling. The first step into the static model is the data preparation and interpretation. We have some raw data like seismic, we have seismic data and we have logs data. So first of all, you should prepare that data. Should have interpretation for the data before going to the model. Then using the seismic data and using the well correlations, you can go to the structural modeling. Then you can have the fishes modeling and the petrophysical modeling, depending on the core data and depending on the logs interpretation. Okay, the fishes modeling and the petrophysical modeling is done, or we have is underlined by or we can group the two modeling steps into just one step that is called property modeling. After doing the property modeling and distributing the porosity and the permeability into the model, we wanted to know the oil in place or the original oil in place into our field, and we wanted to calculate them. Okay, but you should know that we have some uncertainty into the porosity and the permeability and so on. So we wanted to do also the uncertainty analysis. Then the last step before handling the static model to the simulation engineer, it's the upscaling process. Okay, so let's go into details. First of all, for the first step into the static modeling workflow, it's the data preparation and the interpretation. Like what? Like the well logs interpretation. We have some wells that were drilled into our field, so we will interpret the well logs. Interpretation means we will calculate the porosity, we will calculate the saturation, and in some cases, we can also calculate the permeability. For the seismic data, we will do seismic interpretations. Seismic interpretations means that the geophysicist will use the seismic data to interpret and depict the surfaces and the fault locations that into the field. Okay, so we will know the depths at which every well will penetrate the surface or will penetrate the reservoir by using the seismic interpretation. Then we will identify the phases into every well. So every well we have a log, and in some cases we have core data. So by the integration of the cores and the well logs interpretation, we can identify the phases. Like we have sand, we have here coarse sand, we have here carbonate, we have shaly sand, and so on. Then we will do well correlation. What is the meaning of well correlation? Well correlation that, for example, to correlate this interval to this interval. So if we have two wells, so you will say that this interval into the first well is the same as this zone into the second well, and similar to the zone into the third well. Okay, so by well correlation, you can track the zone thickness for each well. Okay, Then also you can do the rock typing. The rock typing is that you will identify the relation between the porosity and permeability for certain intervals into the cored wells. Okay, then you will populate that rock types into the uncored interval and uncored wells. Okay, so as you can see, now we are dealing by well data, just points. We have points into the reservoir. We know the porosity at this well. We know the rock types at this well. We know the surfaces. We know the facies. But we didn't, until now, we didn't integrate the data, and we didn't do modeling step. We didn't do modeling until now. Just we are preparing the data that will be used into the modeling workflow. The second step into the modeling workflow is the structure model. The structure model is to know the surfaces and to know to use the surfaces that were pegged by the seismic interpretation and the faults to have structure model. Structure model, the objective is a structure model, it just to identify the building for your reservoir, like to know that the surface locations, the top skeleton, mid skeleton, the base skeleton, and also the faulting locations. Okay, the faulting location. So you will use the seismic data to construct the building of the model, the building or the structure of the model. Okay, then you will identify or you will define by using the surfaces that were pegged by the seismic interpretation. You will define the horizons. Then the thickness between two horizons is called zones. Okay, so as you can see, we have two zones between three horizons. Then these zones will be subdivided to layers. Okay, so each zone will be subdivided to layers, and the zones are the thickness between two horizons. So that for the structural modeling. Okay, great. So into the software, we are starting by fault modeling. Then we are trying to do XY grading. XY grading is to divide the surface between the upper surface, the down surface, and doing XY grading. That's called the pillar grading. Okay, if it's okay, we can go to skeleton building. If the pillar grading is failed, or we have some distortion into building the XY grading, so we go back to the fault modeling and adjust the faults and see what is the wrong with our fault modeling. Okay, if the pillar grading is okay, we can go to skeleton building. Then we will QC the skeleton. In some cases, we have distortion into the skeleton. So in that case, we will go to the pillar grading and fault modeling to see what is wrong into the pillar grading and the fault modeling. If it's okay, so we can go to the vertical grading. Okay, so as you can see, the structure modeling, first of all, we are starting by fault modeling, then XY grading, then Z grading, okay, or the vertical grading, which is called layering. If it's okay, so we can go to create the 3D grid or the 3D model. If not, so we can go to again to the fault modeling and pillar grading to see what is wrong with the two processes. Okay, so that was for the structure modeling. The third step is the property modeling, and we mentioned that the property modeling has two steps: facies modeling and the petrophysical modeling. For facies modeling, so you will integrate the data from the core. We have a core, conventional core, that was cut into certain wells. So we will have that core data and identify the facies that we are having into that cored well. Then refer by well correlation every facies into the cored well to the uncored well. Okay. So depending on the existing on certain facies into between the wells, so we can say, okay, read, we can think that we have a certain depositional model for the reservoir. Like, for example, we have facies types for the carbonate, okay, like shelf margin, we have shelf lagoon, and so on, okay. Also for the clastic, we have the lacustrine, we have the delta, we have shelf, and so on, okay. So by using the facies from the wells, from several wells into the reservoir, into the area of our reservoir, we can decide that the depositional model for this reservoir is delta fan, or the depositional model for this reservoir is likely to be a channel, and so on, okay. So that is the facies modeling. So for the techniques to model the facies, we have two techniques. We have the deterministic and we have the stochastic. In case that you have dense data, you have high number of wells that were drilled into your reservoir, so you can use that deterministic method. You can use the deterministic method. In case that you don't have dense data, you have just some wells scattered into your field, so in that case you can use a stochastic method. Stochastic means that you will use some statistical algorithmic, like sequential Gaussian simulation, like truncated Gaussian simulation, and so on, to predict the distribution of properties or distribution of facies between two wells at which you know the facies types into this wells. Okay, so that for the facies modeling. Okay, we still into the property modeling. As we mentioned, that the property modeling has two steps. We have the facies modeling and we have the petrophysical modeling. Okay, the second step into the property modeling, which is petrophysical. Petrophysical, usually we are distributing the porosity and the V-shale, into a 3D model. We calculate the porosity or the effective porosity from our well logs. Okay, we have like five wells penetrated our reservoir. So using the triple combo or the logs that you are having into these wells, so you will calculate the porosity, okay, into these wells. Then by using the porosity into these wells, you will distribute the porosity into the 3D model, okay. You will ask now about the permeability. What about the permeability? After distributing the facies into the 3D model, you will also distribute the rock types. So depending on the distribution of the rock types and the distribution for the porosity, you can have distribution for the permeability, or calculate the permeability depending on the type of rock type for each cell, and depending on the value of porosity in each cell. Okay. Also the same for the petrophysical modeling. We have deterministic and we have stochastic. Deterministic means that you will average the values between two wells to have the value into some point at which you don't have any wells. Okay, that is the deterministic. For stochastic means that you will apply or you will use some statistical algorithms like Gaussian simulation and so on to distribute the porosity or distribute the V shale or distribute the saturation or any kind of property that you want to distribute using the stochastic. Okay, when to use the deterministic and when to use the stochastic. In case that you have dense data, you have high number of wells drilled into your field, so you will use deterministic methods like ranging and moving average. In case that you don't have dense data, you have just some wells into your reservoir, so you will use the stochastic method. Okay. Okay, great. So now we did the structural modeling, and we distributed the phases, and we distributed the porosity and the permeability into our model. Okay. Now we want to calculate the oil in place. We want to calculate the oil in place. Okay, great. First of all, we want to see the equation for the original oil in place. Okay, as you can see, that is the parameters incorporated into the equation. Okay, like we have the porosity, we have the water saturation, we have also the thickness. Okay, and we have the beta O. Okay, great. So now we are talking about a static model. Okay, so the static model, we have the porosity, and we have the thickness. Okay, so let's ask a question. Let's ask a question here. We know the porosity at the well location, but what about the porosity into the location without any wells? We mentioned that we use some algorithms like stochastic or deterministic methods to know or to predict the porosity at points at which we don't have any wells to tell us the porosity values at these locations. Okay, so we have some doubt, we have some uncertainty into the porosity that were distributed. Okay, great. So if we used that equation, if use that distributed values for the porosity into the porosity for each cell into our reservoir model, we will have just one value for the original oil in place. Great. What if our prediction is wrong? Okay, so we do uncertainty analysis. We have range for the porosity. We have a range for the prediction of the porosity. So depending on the range for this prediction of porosity, we will have also a range for prediction for the oil in place. That is the idea of uncertainty analysis, that you have some parameters and these parameters have certain range. So depending on that, you are having a range for every parameter, so you will have a range also for the result, which is the oil in place. Okay, so that is the uncertainty analysis in case of a static model. Okay, usually we are using it for the oil in place, calculation. Okay. Okay, so for example, how we can do the uncertainty analysis. First of all, you should identify the parameters that greatly affecting the oil in place or the original gas in place. Okay, like for example, we have the oil water contact, we have the porosity, we have the distribution of water saturation, and so on. Okay, then this kind of analysis is called sensitivity analysis. Sensitivity analysis means to identify the factors that greatly affect the result that you are analyzing. Okay. Okay, great. Then you will assume range for these parameters and then calculate the oil in place. So at the end, you will have three cases. We have minimum case, you have mid case or most likely case, and you will have the highest case. Okay. So in case of oil in place, you will report rather than just one value for the oil in place, you will report three values. You will have the minimum, you will have the maximum, and you will have the most likely value. Okay. Okay, great. So at this step, we distributed the phases, we distributed the porosity, we did the structure modeling, and also we calculated the oil in place. And now we wanted to handle our static model to the simulation engineer, Okay, great. But into our model, into our geological model, we have high number of cells. We will have high number of cells, several millions of cells. Okay. If the simulation engineer will use this static model, this high resolution static model into the simulation or into Eclipse software, so it will require high time to run just one case. Also, it will require high capabilities regarding to the PC. Okay. Okay, great. So in case that you have limited resources for the PC capabilities, and we have just limited time to run the simulation, so we are doing the grid upscaling. Grid upscaling means that you are converting this high resolution geological model to a low resolution, to low number of cells grid. Okay, so you will average just, for example, you will average every 4 cells to represent just 1 cell into the simulation grid that will be used to run the simulation cases. Okay, that is the grid upscaling. Okay, let's ask some questions, or let's revise our service about upscaling. Why upscaling? Upscaling is done because or to reduce the number of cells into the geological model, so that the simulation engineer can run this model into the his software or the Eclipse software or with limited PC capabilities. Okay, let's ask the second question. So the upscaling is a must? No, the upscaling is not a must. Why? Because nowadays we have high PC capabilities. And also in terms of softwares, the softwares also enhanced its capability to run smoothly the calculation for the numerical simulation. Okay, so in case that you have high PC capabilities, so you will run high number of cells models also in low time. Okay, so before doing the upscaling, you should ask yourself about the capabilities of your PC and the capabilities of the software. Okay, so nowadays some companies are not doing the upscaling, and use the same static model to run the dynamic simulation. Okay, so now we finished the dynamic modeling workflow, and now the simulation engineer or the static model was handled to the simulation engineer. The first step that the simulation engineer will do is to QC the static model, because if we have any mistakes or we have something that should be modified and we didn't do these modifications, so the static model, these errors or these mistakes will affect the dynamic reservoir simulation. Okay, the second step is to use the traditional simulation toolkits like the material balance, like the well test, like the decline curve analysis, and so on, to know just rough estimations about our reservoir, to have a conceptual model, We have conceptual model into the static model, the static modeling, we have the conceptual model for the depositional environment for our reservoir. That is into the static model. Also, the simulation engineer should have conceptual model about his reservoir using the traditional analytical methods like the material balance, well test, decline curve analysis, and so on. Okay, great. Then we have some data that we require to run the dynamic simulation, which are the BVT and the scale data. Okay, but as you know that the BVT and the scale data are done by the laboratories, but we can't use this raw data directly to the simulation. Okay, so the simulation engineer will do some modification to the lab data before using it into the simulation. For example, for BVT, he should do adjusting according to the production facilities for the field, okay, for the beta O and RS before using them into the simulation. Also for scale data like relative permeability and the capillary pressure. For relative permeability, he is doing normalization and denormalization process. And also for the capillary pressure, he should do the normalization by the J function and the other method. Then after that, we are ready to run the history matching. Okay. Then after the history matching, we will use the reservoir model, or the reservoir model now is ready to predict the production. Actually, the production prediction is the main goal for reservoir modeling. Okay. Then after production prediction, we will do also uncertainty and optimization analysis. Okay. So for static modeling, we did the uncertainty usually or mainly to the oil in place. For the dynamic, we will do also uncertainty, but the uncertainty in this case for the cumulative production, reservoir pressure, and so on. Okay. First of all, or first step for the dynamic modeling workflow is the static model QC, the static model QC. So some aspects for static model QC, like for the structural modeling, is the structure modeling or the grids are oriented into the direction of the flow or not. For example, we have two models here. We have injector and we have producer. Okay, we have two cells orientations. We have here, and we have the cells are oriented into the direction of the flow. When we inject water, so the water will go into that direction. Okay. Okay. What is the best to have to use this reservoir or this cell orientation, or to use this orientation? Usually the structure model should consider that the cell orientation should be into the same flow direction, Why? because if the cell orientation is not the same as the flow direction, so in that case it will lead to pushing additional flow or additional fluid towards to the production wells. So as you can see, that is the blue for the north-south reservoir model, and here the red one for the aligned with the flow direction. So as you can see, for the north-south that not aligned with the flow direction, we have higher flow or higher fluid production than the reality or than the actual. Okay, so you should consider, or the static model should be QC. For example, the cell orientation. We have also We have also other aspects. For example, if the upscaled properties are upscaled properly to represent the same log interpretation results or not, okay? That also an aspect for the static model QC. Also, after upscaling, is there any difference into the oil in place between the upscaled model that will be used in simulation and the fine model that was created by the G&G team? Is there any difference into the bore volume and the oil in place? Okay, so that also one aspect for the static model QC. Okay, the second step for the dynamic modeling is to use the results for the traditional reservoir engineering tools like material balance, decline curve analysis, and so on, to see or to direct or to have conceptual model for our reservoir, okay? To compare between, for example, if the material balance is telling us that we have 100 million oil barrel into our reservoir, what is the result of reservoir modeling? It is the same, or it is a bit higher, or it's much higher, okay? So we can compare into that cases, okay? So the traditional RE tools can give us a rough estimation for the properties for our reservoir, like in case of well test. The well test will tell you about the average permeability of your reservoir, okay? So you can compare between the well test permeability, which representing the permeability around the well, and the permeability that were distributed into the 3D model. If the average is the same at the well test permeability or it's different, okay? So as you can see, the traditional RE tools will be very beneficial for reservoir modeling. Also for BVT and the scale data. For example, the reservoir flow type will direct us to use certain types or certain unconventional methods for reservoir simulation. For example, if you are having gas condensate reservoir and we have black oil reservoirs, okay? The two reservoirs have different methods for running the simulation. For gas condensate reservoir, we will use compositional simulation. We will use E300 software, okay? For the black oil, which having like API of 24 or so on, we will use the conventional black oil Eclipse or E100, okay? So as you can see, for the BVT, will direct us to the type of the simulation that you will use into running the dynamic simulation. Also, you should do adjusting for the BVT data to adjust the beta O and the RS values according to the production facilities that you are having into the oil field. For the scale data, like the relative permeability and the capillary pressure, for the relative permeability, you should do normalization and denormalization. The relative permeability will control the moving of different fluids, okay? So depending on the value for the relative permeability, you will produce more oil or more gas or more water, okay? Also, the capillary pressure is very important into distributing the saturation into your reservoir model, okay? So also, you should consider the importance and the accuracy for the capillary pressure into the dynamic modeling, okay? If we have several capillary pressure curves from different plugs, so you will do normalization to have just one curve for capillary pressure that will represent all the reservoir cells. In case that you wanted to have high resolution for the capillary pressure, so you can use the J function. Also, in case that you want to have more resolution, you can do rock typing, and for every rock type, you will assign J function curve, okay, and so on. Then after QCing the static model, after using the traditional RE tool that give us a conceptual model about our reservoir, that give us the information of connection for several faults, after giving us a rough estimation for the oil in place and so on, after entering or inputting the PVT data and the scale data. So now we are ready to go for the history matching. What is the history matching? The history matching is that we have actual production from our field, okay? And when you run simulation, you will have a production from your reservoir model. Then we will compare between the simulated production and the actual production, okay? If they are matching, okay, so you can say it's okay and our reservoir model is accurate and we can use it into the prediction. In case that you have mismatching, you have difference between the simulated and the actual production, so you will go to modify your reservoir model. You can modify the relative permeability. You can modify the leaking or the connection for the faults. You can modify the wells skin factors and so on, okay, until matching the actual production, okay? And we have two phases or three levels for history matching. We have pressure match, we have saturation match, and we have well productivity index matching. For pressure match, in case that you wanted to match the average reservoir fluid, you can modify the aquifer size, you can modify the pore volume of the porosity distribution, you can modify the compressibility, okay? In case that you want to have regional pressure, you want to have match for the regional pressure. For example, if you have a certain pressure for each segment for your reservoir, so you can use some factors or you can modify some factors and so on, okay? That is the pressure match level. After achieving match in terms of pressure, you will go to the next level, which is saturation match, which is to match the production for each well, and first to match the production from the field, match the field production, then match every well production, okay? How we can do that? By manipulating the vertical permeability, the shale barriers, and the productivity for the wells, and so on, okay? The third level, which is the well productivity match, okay? In case of well productivity match, you can modify the skin factor, you can modify the permeability around the well, you can modify the well productivity index, and so on, until matching every well production and every bottom hole flowing pressure for each well, okay? For example, if we have this case, we have the water cut from the simulated and from the actual water cut, okay? As you can see, you have nearly the same slope, okay? But the start of water production is different between the two wells. So as we mentioned, the relative permeability is the main controller for production several phases, okay, or several fluids. So in that case, you will say we want to modify the relative permeability to have match between the simulated and the actual water curve. If you have the same slope, so the problem with the endpoints for the relative permeability, okay? If you have the same start but different slopes, so you have a problem into the endpoints, and you have the problem with the endpoints and the Curie or the exponent for the relative permeability curves. Okay. Okay. So after achieving the history matching, so the next step, which is the main goal for reservoir modeling, which is the production prediction and the field development planning. What is the main goal for the field development planning? In case that you wanted to compare, you have a suggestion to apply water injection or gas injection, okay? So you will run simulation case for, you will predict the production in case that you apply water injection, and run another simulation case in case that you are applying gas injection. Run another simulation case in case that you drilled more wells. Then compare the production from the three cases, okay? The case with the highest production. So, for example, if the water injection achieved the highest production, so you will say, or you will propose that the water injection is the best mechanism for developing our reservoir, and so on, okay? That is for the production prediction. Okay? Then also as we mentioned, that we have also uncertainty and sensitivity and optimization for the dynamic model, like we did uncertainty analysis for the oil in place for the static model. Okay, what is the difference between sensitivity, uncertainty, and optimization? Sensitivity is to define the factors or the parameters that greatly affect a certain parameter or a certain variable. For example, we have different parameters like starting oil production, like number of wells, like the well productivity index, like the water injection rates, and so on. Okay, and you want to know which parameter that greatly affect the cumulative production. So that is the sensitivity analysis. Uncertainty analysis, you will have some parameters, like we have, for example, we have two parameters that greatly affect the cumulative production, like the starting oil production and the water injection rate. Okay, so we have a range for the starting oil production and the water injection, and we want to know the effect of this ranges for the starting oil production and the water injection rate on the cumulative oil production. Okay, so you will do the uncertainty analysis. For optimization, in case that you are doing history matching, optimization means that you are automatic, or you are doing assisted history matching or automatic history matching. Okay, you will give a certain range for the factors that should assist in doing the history matching to the software, and the software will have try and error, will have many trials until achieving the history matching. Optimization in case of prediction, for example, for water injection rates, or the number of wells. Okay, so the software will do several simulation runs with different number of wells, with different water injection rates. Then at the end, the software will tell you the best number of wells, the optimum number of wells, and the optimum water injection rate. Okay. For example, as you can see, we want to know the effect of the height of our reservoir, the gas oil contact, the production rate, and the injection bottom hole pressure. We wanted to know the effect of the 4 parameters onto the oil or the cumulative oil production. So as you can see, the factor that greatly affect or most effective on the oil cumulative oil production is the thickness of the reservoir, then the gas oil content. But the production rate and the injection bottom hole pressure having minor effect on the cumulative oil production. Okay, that is for some case. Okay, for the answer, an example for the uncertainty analysis, you have a porosity range like from 18 to 25, and in oil water contact we have a doubt that from the oil water contact depth is ranging from 2000 to 2100, and we wanted to know the uncertainty, the effect of uncertainty in oil water contact and the porosity on the resulted oil in place or the cumulative oil production. Okay, that is one example. The other example that we have uncertainty into the reservoir properties, reservoir permeability, relative permeability curve, skin, drilling error, and we want to know that uncertainty on the well rate, For optimization, as we mentioned that the simulation we have in this case, as you can see, we want to know which optimum injection rate to have the highest oil rate. So as you can see, we have 10 cases, and for each case we have a different injection rate and we have field production rate. So at the end we will select that case that having the highest or the optimum cumulative oil production. Okay, depending on the injection rates. Okay, so in the end, the main point that you want to know about that webinar, that we have some steps for static modeling, and we have some steps for the dynamic modeling. For static modeling, we will prepare our data and interpretation and do interpretation for the data that should be interpreted, and then we will do structural modeling, phase modeling, petrophysical modeling, and then do uncertainty analysis to calculate the oil in place, then do upscaling, and then handle the static model to the simulation engineer. The simulation engineer, first step that he will do is to QC the static model using the traditional reservoir engineering tools to have conceptual model about his reservoir, then enter PVT and scale data, then do the history matching. Then after achieving history matching, he will do production prediction and do uncertainty and optimization for the field development plan. Okay, so that was the end for the webinar, and I will be more than happy to have some question about the webinar. Okay, if you have any question, please drop it into the Zoom chat. We have a question here. When we will use streamlines? Streamlines actually, it will tell you about the direction of the flow. Okay, so we can the simulation engineer can use the streamline simulation to identify the direction of the flow. Okay, and compare between the direction of the flow and the cell orientation. Okay, the cell orientation into the static model. If it's okay and it's matched, so we can say, okay, the static model, the cell orientation is perfect or is optimum. In case that we have high difference, so we can do or modification to the cell orientation. Okay. In the last slide, our choice depended on the cost function also, or only the injection. Here into the last slide, as you can see that we have here the field production rate. I think that in that case, the software selected the optimum injection rate and the optimum field production rate that will lead in the end to the highest cumulative oil production. Okay. What is the difference between classical workflow and modeling workflow? I think that you are talking about the traditional tools. Traditional tools like the material balance, like the well test, incline curve, and so on. Okay, the modeling, like when we have a 3D model for our reservoir. Okay, so the 3D model will tell us or will incorporate additional complexity and additional resolution that will lead into high accuracy for the results. The QC for the upscaled data. For the upscaled data, you should compare between. You can compare between the well log, the well logs and the upscaled value. If they are near to each other, so it's okay, and we can say that the upscaling is okay. But if we have high difference, so in that case, you should do or you should repeat the upscaling. How can we reduce uncertainty into static models? By two steps. The first step is to integrate many sources of data, like in some cases into modeling the porosity, we are using the seismic data. Okay, the seismic data will be a secondary factor into distributing the porosity, so it will lead to more certainty into the porosity. Okay, that is the first step, is to integrate several sources of data. Okay, the second step is to have more data. For example, if you are using just the log interpretation without core data, so into the next wells, you should recommend to have core data for routine core analysis and also for special core analysis. First, why using NT while using Mr. Salah, I didn't understand your question. Why are models important to geologists? Actually, the models are important to the G&G stuff and also for the RE, because the geologist will recommend the next wells that will be drilled depending on his model, depending on the reservoir model. So if you don't have any model, so you don't have any prediction for the new wells. Okay. How to model the aquifer or its parameter are ingressed into history matching step. The aquifer, we have two types of aquifer into simulation. We have numerical and we have analytical. Okay. Usually we are used analytical aquifers like that, using the models for Carter Tracy, like the other analytical methods or other analytical methods to model the aquifer. Okay, that is the usually that we are using into simulating the aquifer, just to locate the aquifer, then use analytical method to represent the aquifer response. Okay, the other method is to have numerical aquifer, like to represent the aquifer by certain number of cells and incorporate it into the simulation. What is the difference between forward and inverse modeling? The forward modeling means that you have a problem and you are solving it. Okay, you are try to find its solution. But actually into history matching, it's inverse process. Inverse process that you are having the solution, you are having the production, and you are trying to get or to guess the probabilities for your reservoir. Okay, that is why we are calling the history matching as inverse process. Anyone that wanted to connect me on LinkedIn, it's no problem, inshallah. Okay. Why using normalized BC or relative permeability instead using for each curve? Actually, for capillary pressure and relative permeability, we have many blocks, and each block have its own relative permeability and its own capillary pressure. Okay, and we want to have one relative permeability for all the reservoir model and one capillary pressure curve for all the reservoir model. Okay, that is the objective of normalization for capillary pressure and relative permeability. But actually nowadays we can have a capillary pressure curve and relative permeability for each zone, for each cell, but it will lead to higher time into running simulation. Okay, so you have the two options. We have another question. What is the accurate data, well log or core samples, and what is the very cost process between them? What is which? I think that you are asking about the accuracy. Okay. So for core samples, as you know that the core samples, you should correct the core sample results regarding to the pressure and regarding to the clay content and so on. Okay. So the more accuracy in terms of, for example, for the porosity. Okay, you have a porosity from the well log and we have the porosity from the core sample. Okay, the core sample porosity should be corrected to the pressure to compare between the well log porosity and the core porosity. Also, you should QC the core or routine core analysis or the core plugs after drying and cleaning the process. Okay, because the drying and the cleaning process can lead to losing some clay minerals, and losing some clay minerals will lead to additional porosity. Okay, so in that case, the porosity from the core sample won't be representative to the reservoir, and you will have a difference between the well log and the porosity. Okay, that is in terms of porosity. Okay, we have also the water saturation. The water saturation that is coming from the well log, you will ask about the parameters that were used into the Arch equation. Okay, the parameters that to compare between the water saturation coming from the well logs and coming from the core samples, you should first correct the constant into the Arch equation that will be used to calculate the water saturation. Okay, so we have many measurements for the core samples, and we have that should be compared, but you should consider the conditions at which we measured that that experiment. Not using upscaling because upscaling distorts the final. Is there any way not using upscaling? Yes, I mentioned that in case that you are having high PC capabilities, okay, that can run your model, so you shouldn't do the upscaling. Okay. Is it possible to build the model without core data and the uncertainty of log data can be handled into the history matching step? Yes, you can do. You can do. You can do model without core data, but it will have higher uncertainty. Okay. Is there any difference between coring and logging? Coring is to get a core sample. Logging is to run logging tool into your well. What is tank model? Tank model, that is the material balance equation calculations. What is other using than distribute distillation? Relative permeability is used to simulate the flow of different fluids at the same time, like that you are having oil and water. Okay, the relative permeability will determine the percent for the oil production and the water production. Capillary pressure is used to distribute the saturation. Okay. Without seismic data, all this modeling will be able to be made? I think no. Or we will, in that case, we will have very, very high uncertainty without seismic data. Just to have to use the well tops to create surfaces, I think it will have a high uncertainty. Think that anyone have any other questions? Okay, I think that we finished our webinar. Someone asking about the last slide. Okay, as you can see here, I think that we have typo here, which into optimization, we are having two parameters. We are having the Q injection or the water injection rate and the field production starting rate. Okay, and we wanted to optimize the two parameters to achieve the highest cumulative oil production. Okay, the highest cumulative oil production. Okay, I think this row is representing the cumulative oil production. So if the starting rate for the production is about 80,000, and that is the water injection rate, so it will lead to the highest cumulative oil production. Okay. Okay. So we are optimizing the water injection and the production rate. Okay. To achieve the highest cumulative oil production, not as I typed here, highest oil rate. Okay. I think it's clear now. Anyone has any question? Okay. So I finished today, and thank you all, and hope to see you into next webinar, inshallah.